Again, this is a new notation now, but it's also a new idea, it's one that we haven't discussed yet. Namely, the notation that I want to describe here is what's called the integral of g of x dx. And I'll denote that by a function capital G of x. So it's you start with a function g of x and you produce a function capital G of x, which is called the antiderivative of g. Notice there's a differential sitting in here. This symbol, this guy here, is called an integral sign. Or an integral, or this whole thing is called an integral. And another name for the antiderivative of g is the indefinite integral of g. And I'll explain to you why it's indefinite in just very shortly here. Well, so let's carry out some examples. Basically, what I'd like to do is as many examples along the lines of all the derivatives that we derived at the beginning of the course. In other words, in principle, you want to be able to integrate as many things as possible. We're going to start out with the integral of sine x dx. That's a function whose derivative is sine x. So what function would that be? Cosine x minus, right. It's negative cosine x. All right? So negative cosine x differentiated gives you sine x. So that is an antiderivative of sine, and it satisfies this property. So this function, capital G of x, equals negative cosine x, has the property that its derivative is sine x. On the other hand, if you differentiate a constant, you get 0. So this answer is what's called indefinite because you can also add any constant here, and the same thing will be true. So C is constant. And as I said, the integral is called indefinite, so that's an explanation for this modifier in front of the integral. It's indefinite because we actually didn't specify a single function. We don't get a single answer. Whenever you take the antiderivative of something, it's ambiguous up to a constant.